Okay, good morning, everyone. It is a great pleasure to introduce Professor Yuval Cassuto from Technion. I've known Professor Cassuto for a long time now, and it's always, his talks are always extremely informative, and I always look forward to learning something new from Professor Cassuto's talks. Just a bit of a biography. Professor Cassuto earned his PhD at Caltech University, yes. Then he worked in industry for a few years before joining the faculty at Technion, where he is now a tenured professor. And so Professor Cassuto brings this perspective on both theory as well as practical applications and practical constraints. With his research group, he won several best paper awards, and they always on to some new and great topics. So we are very excited and honored that you took the time to present in our seminar this morning. So welcome.
Thank you. So thank you, Lara, for inviting me, and thank you all for coming this late in the week and this early in the morning. You are special. There's no traffic, so the special people come to seminars in the morning, so thanks. So yeah, the talk is about a new scheme we developed for genomic compression for using error correcting codes. There's some things to explain here, so stop me whenever something becomes unclear. But first, some introduction about myself. As Lara said, we like to construct codes, different types of code, to help different applications. And today is one example of an application, genomic data, that we try to help with code. And that's for saying that I'm not an expert in genomic data. We just kind of learn on the go. So if I'm saying something that is wrong, that you know better, just let me know. And after that disclaimer, I can now talk freely about genomic compression. About genomic data, as I'm an expert. So that's a very hot thing, very high importance of genomic data. We all saw the importance in the COVID treatment. There's also more traditional applications like prenatal genetic diagnosis, some more scientific. And ubiquitous is the field called personal medicine. Each of us will get a different treatment based on our genomic content. So that's a motivation to deal with this problem. But before telling you about the solution, if you are in the field of information theory, you may feel uneasy now that I'm talking about information theory or coding theory for a specific application. Because we all know that information theory is very general. We typically don't say what data we are using. We just compress it or protect it. So why, what's special here that we do need to make something special for genomic data? So the answer is twofold. There are two features of genomic data that require specific scheme. One is that those vast similarities. If you look between people, between persons, we have like 4 9 similarities of genomic sequences. And even across species, the similarity is huge, like 97% with the chimpanzee. So that's a very uncommon mode in information theory, those vast similarities, and we want to take advantage of that. The other is not related to the source itself, but to the format that the data is given to us. And that's rather than having to deal with a long sequence as usual in information theory, what we get is some short reads, some fragments taken from random positions within the sequence that is the input to our encoder. While the molecule here is one long sequence, we cannot in practice see it as one sequence. We only can see it as a read using those sequencing technologies that we use. Is that clear? I answered the question why we need the special treatment to genomic data. Great. So what's the compelling reason we need to compress this data? This is then set up in communication. So we go to the doctor and he wants to sequence our genomic information. The problem is the processing cannot be done at the doctor's office. It has to be done in the cloud. And now we have a huge sequence that we need to send over the internet, even without errors. It's a huge problem to send those gigabytes of data across the internet. That's just for one patient. The reason the sequence is so huge, not the sequence, sorry, the input data is so huge, is that we don't just send reads worth of one sequence. We have this coverage. The sequencing machine gives us many versions of each base pair. So we get like a 50 gigabytes order of size of those data that we need to send. So that's in communication. A very similar case happens with storage. Suppose we sequence a full tray of genomic molecules, but we don't process them immediately. We have to store them somewhere. And in the future, someone would ask, please process for me person J. Then we'll read from the storage, the code, and process. Here too, we have to compress the data because we don't want a huge storage cost for that system. Oh, that's a great point because I wanted to say that you may ask how people solve the problem today, because there are some applications that use that. And indeed, what they do is they collocate those expensive $1 million sequencing machines with the $1 million processing server. And when they do it together, we don't have this problem. We just immediately take it out from the sequencer to processing and don't have this problem, but that limits the type of applications that we can use in that with that data. Okay, so what's the challenge in read compression versus sequence compression? Is what we get are those reads. They are from random positions within the sequence, and we don't know the position. And if we try to compress each read individually, of course, it's very weak. We cannot compress sufficiently short vectors. But on the other hand, we don't even know, the encoder doesn't know the position, so it's challenging to try to kind of align it together and make it a sequence out of those reads. So that's the challenge. There are two current leading approaches to solve the problem of read compression. One is reference-free, the other is reference-based. In reference-free, we try to, remember I told you that we have many reads looking at similar positions within the sequence, so we try to group them, cluster them together, and then use the similarity across them to compress them together. Or the reference-based approach, where the encoder and decoder share reference sequence, and then the encoder tries to align each read on the sequence such that it can give the position information to the decoder, and then it can decompress it. The problem with both approaches is that the complexity is very high. Here we have to accumulate many reads and compress them together. And here we have to make the processing of alignment at the encoder, which is very costly in computation resource. So both of those solutions are inadequate if we want to do that as a low resource doctor's office. Okay, so what we propose as our approach, the in-between the two current approaches, and that's to put the reference only at the decoder side. And then we save the complexity of the encoder to do alignment on the sequence, but we do benefit from the similarity. And we didn't invent that approach. If you look at full sequences and not reads, that's a very well-known scheme in information theory, the stepping of coding. And what we do in this work is extend this to read compression. So just to go back to the communication setting, a shared reference, the traditional solution, we have a Y given both to the encoder and the decoder. The compressor, the encoder, uses Y in the function, and also the decoder uses the same Y, and then it can recover back this batch of reads that we had in the input. And what we assume about this Y is that it has a similarity with respect to the reads that we see at the input. Similarity means that we have few differences. And differences here is both substitutions, deletions, and insertions. Different types of differences, but the key is that it's not too many. It's bounded or it's low probability, such that we benefit from having Y to decompress X, the batch's Xi, the batch of Xi. What we suggest is to remove the Y from the encoder, then we'll gain in this complexity saving. But there's another advantage of privacy. Suppose that Jane goes to the doctor, her sister has her genome at the cloud, but the sister doesn't necessarily want the doctors of Jane to have access to her genome, and then we basically got this privacy. We can benefit from Jane's sister DNA without having share it with the doctor of Jane. Okay, is that clear? So now I'll turn to the solution. At the high level, when I say our solution, it's mainly my student, Yotam. He's blocked by the Zoom. So what our solution is, first let's see it kind of at the high level. We take those reads that we get in the input, concatenate them to some vector chi, and do a simple matrix vector multiplication, and that's the output. So you already see that in terms of complexity, it's much simpler than all previous schemes. Just a simple matrix vector product, no need for searching, clustering, all the fancy stuff people are doing today. It's very simple. We send it over to the decoder, and most of the work will be done there. But remember, the decoder is in the cloud, so less of a problem. Now, what's the components of H? We'll see. I will not say it now. I'll save it for later. But we have like 4 different codes or subcodes that we use in our construction. Each one is in charge of a different feature of the scheme, which we'll understand soon. Questions so far? Okay, great. So a bit background before I, yes. Oh, I will explain that. That's just at the high level water solution, just to tell you that the complexity issue is solved. Yeah, I didn't tell you how it works, if it works, and we'll see it later. But before I tell you about the solution, let's get some background. Classical method to use channel codes for distributed source coding. It's called coset coding, or it has different names. Basically, if we have, and that's for full sequences. Here's the no reads, just full sequence Y. And we are told that this Y is close to X, to the input sequence, in the Hamming sense. The Hamming distance between X and Y is bounded by at most 1. And if we are told that, what we need to do is take a channel code, an example shown here, with the code that can correct one error, but use it a bit differently than in channel coding. What we do is we use it to partition all the vectors of length n to coset by this code. And now we have a very simple encoding and decoding. Encoding is basically look for our input and just take as output the coset of that vector. So encoding is just taking this column. And then decoding, which we call it in this talk reconstruction, because decoding here has many tasks to do. The specific task, which we call reconstruction, is to use S together with the reference Y, the decoder, to get back X. And what we do, we use a very similar decoder to channel coding, basically to search for a word in the coset S that is close to Y. It's very similar to error decoding in channel coding, only that instead of using coset 0, we look for words in coset F. Okay, is that clear? That's kind of a common scheme. It was it's classical. It's even from the 70s. Weiner already suggested it, but there were some works 20 years ago about how to make it practical and or also better understand the theory of this scheme. So that's an important background. Another useful background is generalized concatenation. It's a form of concatenation of code that is more flexible than the classical phonic concatenation. The reason I have to tell you about that, because our construction uses this form of concatenation. Basically, what we do, we represent our code word as a matrix. And now the way we encode, we generate an inner code parity check matrix, but it's not just one matrix. We slice it to multiple slices. It's general for a general number of slices. We can do that. And now the way the code is defined, that each slice gives us R1 bits. Think of those as syndrome bits, but just of one slice. And what the code tells us is that the R1 or Ri syndrome bits of slice I needs to be in an outer code of redundancy row I. That's a scheme from the 70s. It's also similar to, maybe you heard of tensor product codes by Wolf, which is a special case of that. But that's a... Yeah, that's a parity check matrix of just the inner code.
And so when you talk about the thing
Exactly. The rows of the parity check matrix generate Ri bits. And we need to constrain those Ri bits from all the inner blocks, inner subblocks. So here we kind of concatenate many inner subblocks, and they need in slice I to satisfy the constraint of an outer code with redundancy row I. And the way it's used in practice is we kind of do a hierarchy where the inner codes become stronger, right? When you add more slices, the inner code becomes stronger. But notice that at the same time, the outer code becomes weaker. And if we kind of organize it nicely, we get a code with a high minimum distance, because the minimum distance would be the minimum of the product. So if it's more or less constant, the product between the inner and the outer distances, then we get a code with good minimum distance. But this is a very powerful scheme. It's good for other things, not just getting high minimum distance. And one uses, we will see, that we'll see today. We took, in a previous work, we took this channel coding scheme and used it as a source code, similar to what we are doing here, but without reads. Here it's also a sequence. So what we do, it's a joint work with Jacob Zinn. So what we did, we kind of organized the sequence as a column scan. And we use this generalized concatenation codes to generate the parity bits, parity symbols, which is what we encode. So this is what we send out to the decoder. This stays only at the encoder. It's not part of the code word. And then the rate, the compression rate that we get is the volume of the shaded divided by the volume of the white. And of course, in source coding, lower is better. In channel coding, higher is better. Here, lower is better. So that's an important background, because what we'll do here is generalize that to reads. Question about the background?
So you change the organized sequences and then row by row, that row is a code word, and then you like as the method, then you extend that. Or the redundancy in every single element in the sequence matrix.
Yeah, maybe I cannot explain it in full, but think of taking this same construction, but there's no need to send the white, we only send the shaded. Yeah, it's the same construction. The code is not suboptimal or anything, but the organization, the way it's used, is different. Okay, so what are the components of our scheme? We have 4 steps that we need to do in order to get a reliable reconstruction. These steps refer to the decoder. So first thing the decoder has to do is alignment. When I say alignment, I mean to slide something, not the read itself, because we don't have it yet, but we want to slide something that we'll explain later about the full reference sequence, and looking for matches, looking for positions that are interesting, that are useful for the reconstruction, which is the next step. Once we found a useful position within the reference, we do the usual thing of reconstruction. We use the syndrome that we got from the code word and the reference segment, just a specific segment that we found, to reconstruct the read X. But that's not enough. In some cases, we will have problems in those first 2 steps. And then we need also validation. We need some step that will tell us that we did well, some go, no go type of check. And after that, we have this outer code. All those first three steps were about the inner, the subblocks, each read individually. But because sometimes we will fail or we have errors in some of the reads, we need this external, like outer code that will correct those, such that we get with high probability all the reads perfectly reconstructed. And those 4 steps correspond to exactly the 4 components of the parity check matrix that I showed you in the beginning of showing you the solution. Questions? Good. So now let's try to cover.
Seems to be at some point why? You're calling a reference.
No, it's not reference free. It's reference to the decoder, but the design of those H's does know the similarity model of Y. It knows, for example, we'll see a parameter soon, P, which tells how similar the reference is to our source. That was a good question, because that's exactly the following slide. In our model, we have X and Y, which are long sequences, capital X and capital Y. And here we assume that Y itself, the genome is the IID Bernoulli half. The sequence is not a mandatory assumption, but it's useful for analysis. Now what we get is a read that is a fragment of the long X. And what we are told is that there is some segment in the long reference Y, capital Y, which we call small y, that is similar. Similar means that xi came from yi after going into some channel with parameter p. Think for now about a substitution channel, maybe a symmetric channel with parameter p. So that's what we see here. From small y to small x, we have some channel with parameter p. Here you can see justification. How do we get that? We can think about one channel with parameter p1 as the difference between the reference and this individual genome. That's parameter p1. And there's another channel of for the sequencing errors themselves with parameter P2, and the combined operation is a one equivalent channel of parameter P. So that's the similarity model.
Okay.
Sure.
So you have your reference Y on the other side. Remember, that's pretty similar to Y. You don't know exactly where the differences are. That changes
Yes.
Are we trying to communicate the syndrome that we say? Is it the syndrome associated to a read or a syndrome associated to the big X?
Oh, that's a good point, because the capital X is not explicit here. It's only an implicit sequence.
Right.
All we see are those Xi's, and we see a batch of M of those. So yeah, it's a good, maybe it's confusing, the capital X. This is just to justify how we get this channel. I could just tell you that's the channel, maybe you were happy, but I wanted to justify the entire file. Okay, so what I send is 3 syndromes for one read. These are individual, 3 subsyndromes. Each one has a different role, and one which is shared to all the batch that I'm seeing now.
So for each,
Yeah.
I'm going to say 3 syndromes, and then I also have the other.
Exactly. Good that you asked, because we don't want to miss that. Now the problem is basically get a batch of reads with the decoder has access to Y. Just compress it such that we get the lowest possible rate, but still we are able to reconstruct it with high probability. For that, we define a code with the 4 parameters. N is the read size, M is the number of reads in a batch. You kind of know those. R is the fixed rate compression rate, which is just the ratio between the encoder output and the encoder input size. And PS is another parameter of the reliability of reconstruction. Basically, we want the decoder to succeed of reconstructing the batch with probability at least PS. That's the problem formulation. And what we need is to find a code with encoder and decoder such that we get that. I'll go briefly. I will not get deeper into the encoding and decoding, but what we see here is the blue is inner encoding. The pink is outer encoding, and we see how the inner encoding uses this H2 matrix that is partitioned to reconstruction and validation. But here for the encoder, it doesn't matter. It's one matrix H2. And then the residual, this full matrix is a full rank square matrix. We use the remaining rows to calculate some input that will go into the outer encoding. And the rate, you can see it's very product of the rates. It's one minus the product of the rates of the outer code and the inner code. Decoding has a similar structure, but here we see the 3 different steps that I mentioned before. First, we need to align each read over Y, and now we get a set of, in general, multiple positions within Y that are candidates for reconstruction. Each candidate will go into an inner decoding for reconstruction, and each of them that pass that step of reconstruction will be validated against the special syndrome we include for validation. And the outcome of inner decoding will go to outer decoding through those B syndromes. Sometimes we will not succeed in the inner decoding, and then we'll get the erasure symbol in some of those outputs that we send to the outer decoder. That's decoding. Now let's talk about alignment. Alignment is the step where we take not the read itself because we don't have it, but some sample. You see the light orange. This is a sample of each read that we include in the encoded message. So we slide it over the reference, and now we distinguish between two types of alignment matches. One is we call a proper alignment. That refers to the position within Y from which X is actually taken with this channel parameter P. But that may not be the only position that we find. We may find others, which we call improper alignment. And then these are kind of unrelated, right? If X is not related to Y, you can think about it as coming from a useless channel from Y to X. That's what we call improper alignment. And the idea of the scheme is that we will use the validation to reject all those, such that we only get the proper alignments from which we can reconstruct. Yes.
Seems to me that a priori we do not know even beforehand, so when you have all the samples, how the alignment should be, right?
Yeah, that's the task of the decoder. It slides the light orange bits on the reference, and whenever it sees a match is defined here. We want a small Hamming, if it's a substitution only, we want small Hamming distance between this read identifier of X and Y to be bounded by T, which is a parameter of the decoder. Whenever we find this match, we declare it an alignment, positive alignment, and then there's a proper and there's an improper.
I'm saying, like, even if you have all the reads, that is not enough on its own to tell whether the alignment is proper or improper. Or is it?
Oh yeah, the decoder doesn't know. The decoder, which we only, the designers, we distinguish between proper. The decoder sees a set YI, and it tries all of them. But for us, it's important to distinguish. Yes?
So I used to say that the situation that is problematic is that the proper alignment and the improper alignment have the same Hamming distance from the true sequence. That is the worst case scenario. But it's not also possible that the proper alignment one is T distance, but there's some sequence in there that's T minus 1. So the improper one is closer in distance.
What you suggest is maybe an idea for improvement, but for us, we only care about the threshold. If we are below, not greater than T, we declare it as a candidate, and then we have two types.
Just to follow up on this, so at this point you have a set of candidates, and then you are going to discard some of them on the next step.
Yeah, this inner decoder will reject some, but some will even manage to be miscorrected. For that, we added validation. It will soon be clear why we need these special bits for validation. Think of it as an error detection. Hopefully, most of them will be rejected here, but some will not. Some will still be misvalidated, so which means that the outer code may see also errors, not just erasures of the previous step. Yes.
You're making multiple candidates from the sequence Y.
Yes.
Isn't Y a huge genome? So do you have a way to bound the number of candidates based on, let's say, like how far apart the reads are? Or are you? Because it seems very high complexity to have all the segments of Y to compare to everything towards every read of X. It seems quite large.
You had, one issue is complexity, but remember the decoder is at the cloud. There's a lot of resources, and also the sample, the fact that we use a sample, we just use the small sample of bits that reduces complexity. But another issue that I think you pointed is about if we have many candidates, we may have higher probability of miscorrection, and that's indeed why we need validation bits. Usually in coding theory, we think that miscorrections are rare, But if you have many, like 10 or 100 improper alignments, you really need these extra validation bits to reject most of those. Now the question is, how should we design all this mega code? And we see all those parameters, alignment parameters, inner coding parameters, and outer coding parameter. All those, of course, affect the performance, the probability to succeed. And all those in red also affect the rate. And there's an interesting problem, optimization problem, how to set all those parameters such that we get the objective of minimizing R, such that we satisfy the reliability constraint. That's interesting, but I like it that you are active. So let's skip that because I want to get to the deletion. The interesting thing that I skip here is how we analyze. We have to have some analysis to design all those parameters. But let's skip it because I want to get to the supporting deletions. In reality, genomic data also has the deletions and also insertions. So now we want to extend the support to those as well. So what we address is a model which we call a single deletion, multiple substitutions model, and that's per read. It's not that we have one deletion overall, one per read. The read is relatively short, maybe 100 or a few hundred bits. That means that within Y, one of them may be deleted, that's the underscore here, and a bunch of others will be substituted. So that's an example. The justification is deletions are much more rare than substitutions. And if we need more than one, it's not a problem. We can shrink the read size and get back to this model. And now what we have to do for that case is to extend alignment and extend the reconstruction to deal with those deletion errors. In addition to the substitution errors, we don't forget about those. So what we need, the first thing is an alignment. Yes. Oh, single bit within each read segment. Of course, everything is generalized to a non-binary alphabet, same idea, but bits is easier to think about. So what we need to support alignment with that is find a new alignment metric. The Hamming distance is no longer good. See those sequences, they look very far in terms of Hamming distance, but if you delete the first bit, they're very similar. So that's no good. We need other options. The Levenshtein distance is very good. It's maybe the most natural metric here, but it has very high complexity. And remember, we need to do it for each shift within this, the reference. So that's too costly. A low complexity alternative that was proposed a few years ago is called the shifted Hamming. It has linear complexity, but the problem, which we'll see soon, is that it has high rate of false alignments. So what we propose is a new metric. Maybe I don't have time to explain it in full, but basically we define the function, the phi j's, and this delta of adjacent phi j's, and what we define the metric to be the distance between x and y. And notice that now there are different lengths. Y is n plus 1 length, and x is n. We define it to be some deterministic function minus something that we have to maximize. So we have another step, an extra step of maximizing it across the T. And that's what we declare as the shift compensating distance between X and Y. Now that maybe will not tell you why it's a good idea, but let's see this example. Here we took Y and deleted one bit from it and got X. And what we see here is that until we get to the deletion position, the phi 0 is fixed to 0. It doesn't change. Basically, it doesn't accumulate any substitution. But once we get to the deletion position, it starts becoming unrelated because of the deletion. So we see now increase in the slope half. Well, the other function with the shift is the opposite. After the deletion position, it's flat, but before it had a slope half increase. And what we do, we find this maximal gap between those two sequences. You can see here in the delta function, that's this point, and that's what we declare as the estimate of the deletion position. But we have more than that. We also count how many substitutions we have after compensating for that shift. Basically, we count how many we have. We go from here to the right, plus how many, what height we went from 0 to that point. And here you see the extreme case that this shift to compensating distance is identically 0. Basically, it managed to compensate completely for that deletion. Is that clear? And now we have a metric, deterministic metric that we can use. We also have analysis for it that I don't have time to explain. Basically, if we look at those deltas, we can look at it as a random walk. Oh, I didn't tell you what I'm trying to do. I try to analyze the probability, the distribution of this distance, if we know that X and Y are unrelated. That will tell us what's the capability of this metric to reject false or improper alignment. We get X and Y that are independent IID half, Bernoulli half sequences, and we want the distribution of this shift compensating distance for that. What we observe is that this is a random walk, so we can analyze this random walk combinatorially. Again, I don't have time to explain, but let's jump. We have a theorem that tells the closed form distribution of this dn, which is the random variable of what would be this distance on the sequence of like n and n plus 1. We have the full closed form expression of this distribution. And let's see the results. In blue, we see our metric, and we compare it to the previous metric, which is called the shifted Hamming distance. In green, that's the CDS of those two distributions. And what we see the advantage is this vertical line here. Basically, if we want to reject a false alignment, you want to have high distance between unrelated sequences. So here we have the probability to get at most 4, the relatively low distance is very low in our metric, but if we use the previous metric, it's pretty high. Most of the time you will get very low distance, even though the vectors are unrelated. Well, in our case, it's better. Is that clear? That's the probability to get distance at most, let's say 4, between unrelated vectors. Maybe it will be clearer with this graph. Here we took, again, a random Y, and we deleted one position in that here. And we calculated the distances, the distance matrix on all possible shifts between X and this Y. And what we see is if we use the Hamming distance, we cannot really distinguish. We have some blip here in the correct position, but you see it's very similar to the background noise. In the shifted Hamming distance, the previous one, we do have a 0. Basically, it does find the match, but again, it's not far from the background. The background is very low because of this distribution that we saw before. While in our metric, we get kind of the best of both worlds. We do get 0 at the correct position, but then the background is much higher, so it will be easier for us to distinguish between the proper and improper alignments. Questions? Okay, the problem with the Levenstein distance is that it's more general because it also tries insertion and also deletion. It's not limited to 1. So it may also, we didn't try it, but it may also find a false small distance. Yeah. We need a metric that is targeted for a single deletion. Okay, so we're at 9:50. So should I get 5 more minutes? I'll try to wrap up. So the last thing I have to tell you is now I showed you how we do alignment with deletions. Now I'll tell you how we do reconstruction. And luckily, the problem of reconstruction with deletion we have is easier than the general way in channel coding. Remember, in channel coding, what we have in a deletion channel, we have the input, the code word, then the channel deletes something. We have no idea what happened. We have to somehow use the code to complete what is deleted. What we have here is a different setting. We have a source that was deletes for us from Y to get X. Then the encoder sends the syndrome. And also we have Y as the side information, the reference at the decoder. And if that was the case, we had just those two, we were in a similar situation as in channel coding, but we would have needed coded correct deletions there. But remember, we have this special help that we have, this read identifier. Remember this sample of bits. Together, the decoder also sees that as part of the code word. And the key is that read identifier gives us some hints about where deletion happens. We see it here. Think of Y as a read. It's a zoom in, the Y sequence of the read. It's a zoom in just to see the read identifier. Now, suppose that we have the sampling of bits that we send as the read identifier. And what we do is a similar alignment that I told you before with this new metric. And what the metric found is that T star, the position that minimizes the metric, that's what we look for, is here. Remember, that's part of the alignment. Now I show you how we use that also for the reconstruction. And what we can do is say, okay, if this is the estimate of where the deletion happened, more precisely, if the subsequent bits are the estimates of where deletions happen, let's take all those bits following it, but not beyond the next identifier bit, and declare those as a candidate list for where deletion happened. Basically, we got some hint with high probability. One of those bits is the one that was deleted. Basically, we cannot distinguish between anything happening between two orange bits. So what we do, we'll use them all as candidate list. And now we can invoke the inner decoding for substitution only on each of those candidates. And then after we try them all, we can apply a majority on the outcome and declare that as the most likely reconstruction of what we have here. And the intuition why majority is a good idea. Think about if we mispredicted the deletion position, then we have this property that the effect on Hamming distance, on the number of substitution errors, is kind of graceful. If we perfectly estimated the position, we have no substitution except the original ones by the channel. But if we were mistaken by a bit, let's say one shift to the left or to the right, still the number of substitution errors that we get from that misestimation is small and graceful. It increases as we go far from the true position of deletion. So basically what we expect in all those invocations is that we have multiple words in this neighborhood. So some of them may decode to the same code word, and that may be the correct one. Okay, is that clear how we use the multiple invocations? And basically we can solve it without actually using code for deletion correction and get relatively good results. So now we can summarize. So if I want to summarize the contributions, it's a short list. We have a coding scheme It's efficient and flexible. You can tune everything that you want there. And we came up with an alignment algorithm or alignment metric with algorithm that has a proven detection capability. We can analyze it precisely. Unlike this list, the list of future work is much longer. And each of you may find an interesting thing to work if you want. So one is reducing the coding complexity. We pushed everything to the decoder. We said it's high resource, but we can help that. And one idea is to use graph codes. Currently, we use here basically algebraic codes, BCH codes, but it makes sense to extend it to reconstruction with the graph code. Another idea is to use codes for deletion. It may save us some work or improve the performance. Maybe we can combine different types of code. Adding insertion, very similar, but we do have some extensions to also include insertions and also to multiple deletions, but some gaps are there. Some of the things I showed you work here are not as low complexity as in a single deletion. Another idea is instead of here in this work, we did only individual reconstruction. We invoke the decoder each time on one hypothesis, but why do it this way? It's suboptimal. Maybe take all the candidate list of alignment, put them all into the one decoder and let it find the best reconstruction from all this information. We didn't do it at all. It may work nicely. All we assumed about alignment encoding is that this is a sample, some bit sample, but we can do something smarter, maybe parity bits that do more than just sample the code word, maybe can help in the reconstruction as well. That's ideas for the construction. And since I hoped that Rick would be here and he's here, feedback is also a good option. Here I mean feedback both in the traditional operational sense, where the decoder can feedback partial results and get improvements from the encoder, but also internally to the decoder, we may get feedback between the reconstruction and alignment. Reconstruction may fail, and it will tell the aligner, the algorithm that does alignment, maybe try better, try to be more precise, change the parameters, and then go back to reconstruction and hopefully be able to improve the overall performance. So thank you very much. If you want to read more, we have an archive paper telling this story in more detail, and some ISAT previous papers. Thank you very much.
Super informative talk as always. We have time for a couple of quick questions. There's someone else here coming right after us at 10 o'clock. So we can continue discussion outside of this room, but while you're still here together, if there's any quick question for Professor Cassuto. Yes, please.
Yes, so the fact that the reference, so if it is rather than it's like instead of is a journal hourly.
Yeah, basically you need to say what P is. P is the parameter, and you are right that in practice, someone will have to tell us what's P. But you can try, and if it doesn't work, you can, it's like a knob that you can tell, okay, let's try a higher P.
And then what is this thing?
Oh, P appears, the part is skipped. P appears in all the analysis. There are a bunch of failure probabilities. Yeah, failure here, and also the parameters of the code need to fit P. If P is large, you need a stronger code. So you pay in rate and also. No, we didn't do like a symptotic analysis. We have a scheme that works for general. Yeah, maybe there are also theoretical, like fundamental limits of alignment with the reconstruction. Yeah, we didn't do any of this. Okay.
Much, everybody. We're right on time. So, thank you for attendance, and I hope I see many of our students and colleagues in San Diego at ITA next week. And have a good rest of your week, everyone. Thank you.